Refraction notes. Start off with some vocabulary. When light hits a medium, there's one of three things that can happen to it. It can reflect, bouncing off the surface, such as on a mirror. It can absorb or soak into the surface. Or it can transmit and go through. Pause and copy. For light that transmits and goes through, it is subject to refraction. When a wave changes mediums, its speed changes and it causes its direction to change. It bends. Snell's law predicts how much it's going to bend. This is Snell's law. N times the sine of the angle equals N times the sine of the angle. The book usually uses ones and twos down here. I like to use letters that represents the mediums. I use A for air, G for glass, W for water, etc. So N is called the index of refraction, and basically it's telling how much is the light going to slow down in that medium. This is the relationship. The speed inside the medium is the speed of light in a vacuum divided by N. Remember, the speed of light we use 3 times 10 to the 8 meters per second. There's a couple N's we should know. N for air is always 1.0. It's the same as N for inside of a vacuum. This number will never be given to you. You are expected to have it memorized, and it will be used in any Snell's Law problem. N for water is 1.33. This one they won't have you memorize, but it's a good one to know the value for. N for glass is usually around 1.5. Pause and copy. So we're going to make a diagram. This represents some glass, and we'll have a light ray coming from the air down into the glass. Let me zoom in here. This is our incident light ray. Incident means it's incoming, so the light ray is coming into the surface. Right where the light ray strikes the surface, we're going to draw an imaginary dotted line. This line is called the normal. It has to be perpendicular to the surface right where the light ray strikes it. Now this light ray is going to bend when it comes into the glass. Bending is called refraction, so we call this the refracted light ray. Now the purpose of the normal line is to measure our angles from. So if I measure the angle up here from the normal to the incident light ray, this is theta I. We call that the angle of incidence, I for incidence. Down here we're going to measure the angle from the normal to the refracted light ray. That's theta R, and that stands for the angle of refraction. Pause and copy. Let's look at a sample problem. A light ray is coming in from the air at an angle of 25 degrees to the surface of the glass with an index of 1.55. What angle does it come out? So we're going to be using Snell's law. I have A on here for the air side and G for the glass side. We know the N of the air is going to be 1, and they gave us the angle 25 in the air. We're looking for the angle in the glass. So we're going to be solving the equation for theta glass. We're going to divide both sides by N for the glass, and then to find the angle you have to do the inverse sign. So our equation will look like this. Now our N is 1.0. You have to have that memorized, and 1.55 on the bottom, and 25 degrees looks like this. To calculate on your calculator the inverse sign, you're going to be hitting the second button first and then the sign. And then inside the parentheses, we have 1 divided by 1.55 times the sine of 25. All right, so we get 15.82243. And then we're going to round this off. Our index is 1.55. That's considered to be a constant. We don't count that when we're doing our rounding. The measurement is the angle. The angle is measured to 2 places, so we're going to round this to 2 places, 16. Pause and copy. Bending. For light going from a lower N, such as air, to a higher N, such as glass or water, it's going to bend toward the normal line. This is because the light ray is slowing down. For light going from a higher N, like glass or water, to a lower N, like air, it's going to bend away from the normal line. That's because the light ray is speeding up. All right? These two relationships need to be memorized. Pause and copy. An easier way to remember that is that the angle in the air always makes a larger angle. To remember these rules, I go back to some stories from my childhood. As a young lad, I used to like to ride my skateboard out on the sidewalk, and on occasion I would run off the sidewalk into the grassy area. Now the sidewalk is smooth, and so I'm moving nice and quickly there, and then when I go into the grass, which is rough, I slow down. So the skateboard slows down, but because of inertia, I keep flying forwards and fall off the skateboard. If we look at my normal line perpendicular to my surface, when skateboard is slowing down, I'm falling towards the normal line. I also enjoyed roller skating as a youth. The first time I went to a roller rink, I had never been on roller skates before. And they give you the roller skates, and they have a little carpeted area for you to put them on. So I practiced, and I went back and forth on the carpet to make sure I could skate without falling before going on to the roller rink. But as soon as I took one step out onto the roller rink, the smooth surface had my feet take off really fast, and because of inertia, my body wanted to stay still. So again, looking at my normal line, as my feet take off faster, my body's falling away from the normal line. So if you slow down, you fall towards the normal line. If you speed up, you fall away from the normal line. All right, let's practice this on an example. I have a light ray coming into some glass, and this light ray is going straight through. Now the only way it can go straight without bending is if the incident angle is 0. If you shine it straight down on the normal, it will not bend. Or if the two mediums have the same index of refraction, and I'll show you some examples of that later on. Because air is 1.0, any medium that it goes into, it will slow down and bend towards the normal line. All right, the next example is if we start inside the glass and we're coming out into the air, instead of going straight, it has to bend because it's speeding up. Speeding up makes it bend away from the normal line. All right, and remember the purpose of the normal line, we're measuring the angle on this side, so bending away is going to make that angle get larger. My shortcut for remembering these is that this angle in the air always has to be larger than the angle inside the glass. End of notes.